Hello everyone, welcome back to part 2 of the uncertainty estimation lecture. In the previous lecture, we were looking into how we estimate uncertainty for one-dimensional signals, and we looked into a few methodologies all the way from base to backprop, Monte Carlo sampling using dropout, and also the heteroscedastic model where we actually predict uncertainty itself. So this lecture is going to continue that a little bit further. We're going to be looking into other ways to estimate uncertainty, but we're also going to see how do we apply these methodologies to imaging data, because that's one of the main topics that we have in this specific module. We're going to look into different dropout models, into using something called M-heads, where you have multiple hypotheses, probabilistic Unet, hierarchical models, and how do we calibrate uncertainty. You've seen this image before. So this image here is showing that there is a way that you can calculate uncertainty on a task. For example, in this case, is a segmentation task. So in the task here, we want to, given this image, we want to be able to label all of these different objects in the image. So this is a ground truth that was drawn by a human being. And this is what the model predicts. So the model is predicting this from this image. And you see that it makes mistakes in different areas, and those mistakes have uncertainty regarding attributed to them. And the uncertainty has two sources. It has the aleatoric uncertainty, which has to do with the data itself, the imaging data itself. Normally has to do with lack of resolution, the amount of noise, the fact that we cannot distinguish between the borders of two objects, for example. All of those things contribute to the aleatoric uncertainty because this is related to the data itself. While epistemic uncertainty, as the name says, is most of the times related to the lack of evidence, so to the lack of samples or something that the model has not learned yet because it doesn't have access to enough samples to be able to understand what's going on. So here there are, for example, issues that you can see below the car where maybe the network has never really seen enough of those. When you are very far away, the network has not seen enough examples to know how to detect those. And further down here, you have a situation where the network cannot really distinguish between the pavement and the road, maybe because the model has not seen enough pavement with this specific type of pattern that we see in this image over here. In this specific setting, there are two types of uncertainty that we normally look at when looking at medical imaging or even non-medical imaging data. So there's the aleatoric uncertainty, which is responsible for any kind of uncertainty that comes from the data itself, from our ability to sense what the environment looks like for noise that the data might have. And obviously the best way to improve on the aleatoric uncertainty is by improving the quality of the data. So aleatoric uncertainty is something that is predicted from the network. You can see it as a new output of the network itself. The other type of uncertainty, called epistemic, is modeling the uncertainty of the model itself, the fact that the parameters of the model are not perfect, and the fact that because of the lack of data, you might be in a setting where the parameters of your model are uncertain. You are able to estimate the epistemic uncertainty by sampling from the model itself via things like, for example, the use of dropout at test time. In all of this, the use of dropout, primarily when you're looking into 2D images or 3D images, any kind of image where you have a spatial domain, dropout is not as trivial as when you are using a dense layer. The reason for it is, for example, dropout is a class of methods that creates a random mask which is then applied to the activations of your models. In this specific setting, if you're applying it to imaging data, then the randomness of the domain will cause the situation that you're seeing here on the first image. So if you randomly sample a specific location to null the activations at those locations for a specific probability, let's say a probability of 0.2, you might end up with a dropout mask that looks like this. And the issue of a dropout mask like this is that it creates holes, or it creates zeros randomly in a vector of activations. The problem is the next time this feature map, which is not going to contain values in certain locations, but is going to contain, for example, a zero value in the locations where you see the X, when this map is now fed into the next layer, a convolutional operator is going to do a convolution over this. And obviously the convolution wouldn't make any sense anymore because many of the elements of that convolution are now going to be 0. In order to fix this issue, there are several types of dropout in 2D or 3D that have been proposed. One of them, called spatial dropout or drop channel, as the name says, you drop completely one of the many channels of a feature activation. So you drop every single spatial location of these channels. Another way to do this is called drop block, which is somewhere between classic dropout and drop channel, where you're still dropping locations at random, but the blocks that you're dropping are large blocks of a certain specific size. For example, in this specific image that you see here below, the blocks that we're dropping are 2 blocks of size 4 by 4. And because the blocks are larger, there is more continuity in the features. For example, this part here still has enough spatial features so that the backpropagation gives you reasonable training of kernels. So we're still masking some parts of the image, but we're preserving the spatial contiguity of some other parts of the image. Lastly, you have another technique called drop layer. So drop layer only makes sense if your network is a residual network, because in the residual network, you have the function itself and you have the residual connection. If you were to drop the function completely, the layer completely, the residual connection still exists, so the network will still work. And by doing this, you can actually completely remove layers as a way to introduce stochasticity in the dropout setting. Now that you've seen how do you convert dropout from a one-dimensional vector into a two-dimensional operator, so something that can work on images, let's now try to implement the last network we implemented in the previous lecture, so the one that is using both Monte Carlo dropouts and also the heteroscedastic prediction of the aleatoric uncertainty in the same network for the purpose of imaging applications. So you've seen how would you apply uncertainty in a medical imaging setting, and you've seen a network being trained to predict not only what it's supposed to predict, but also the uncertainty that is associated with that task. We're now going to go through a series of either models of uncertainty or applications of these models in a medical imaging setting that have been published in the past couple of years. So the first of them is a paper from Felix Bragman et al. In MICAI 2018, where they present a multitask uncertainty model. So what is multitask doing here? The aim of this model is to regress out or predict what a CT image looks like and what the segmentation is of a input MRI. So we give an MRI image of the torso, more specifically of the prostate, to a network, and the job of the network is to do two things: to predict the CT, the equivalent CT of the same patient, and to segment this image into the different organs that we care about. The reason that these two things are done in parallel is because if you're trying to treat patients for example, for radiotherapy planning, and you want to do so by planning from an MR image only, because that's the one with the highest amount of tissue contrast, you can then avoid to do a CT of the patient by being able to regress what the CT image looks like, and you can segment by using a segmentation network. And also, the CT that is regressed out can then be used to calculate the attenuation map, which can then be fed into the radiotherapy planning system, and the segmentation model can then be used to create the different targets for the radiation therapy. Because this model is multitask, it's trying to do two things at the same time, it has two separate uncertainties, one for the regression task and one for the segmentation task. And the loss function takes this into account. So you see here, there is the prediction on this side and the ground truth of the CT image, which is modulated by the variance that is predicted. For the segmentation task, what we're doing is we're optimizing for the cross entropy, again, between the prediction of the network and the truth class, which you see here on this side, again modulated this time by sigma 2, which is the uncertainty coming from the segmentation channel. And you have the regularizing term that will stop the sigma 1 and sigma 2 to basically tend to infinity, because this will be optimal for this part of the loss function. The results of this method are quite appealing. I'm going to focus primarily on the visual part of the results. If this is what you would like to predict from an input MRI. So this is the reference CT. This is what the model predicts. This is what you would like the model to segment, and this is what the segmentation looks like, the predicted segmentation. And then you can see that the heteroscedastic, or the aleatoric part of the uncertainty, is localized around the bony regions in the CT regression model, which makes sense because that's the area where you'd expect the biggest differences to exist. While in the segmentation model, most of the errors are around the organs at risk, because you wouldn't expect the model to make, for example, a mistake in the middle of the soft tissue, like this part here. Furthermore, the epistemic uncertainty basically tells you that there's a few areas where the information is lacking, where we will need more samples. For example, here, you see that the prostate has not converged well enough yet, so this still has some epistemic uncertainty, meaning that more examples of what prostates look like would further help the network to reach a better result. Same thing when it comes to the CT regression, so more data should help us reduce this ability to disentangle between soft tissue and bone a little bit better. You also see that the errors between the prediction and the ground truth are highly correlated with the uncertainty that is predicted, the total uncertainty. So we see that where the network makes a mistake, the network kind of knows that the mistake is going to be made because it predicts that there's a high uncertainty. And you can actually go a little bit further than this. You can calculate a z-score. So what the network itself is going to predict two things. It's going to predict the CT itself, right, the mean prediction, but it's also going to predict the standard deviation. And because we have a mean and a standard deviation, so the prediction, the ensemble prediction and the uncertainty of that prediction, we can then calculate the z-score. So how far away is the ground truth from this mean and standard deviation that we're predicting? And you see that for this multitask model, the one that has heteroscedastic uncertainty, the z-score looks very flat and looks really nice, with only a few areas where you're at the edges of the z-score, which is exactly what you'd expect. So you see the blue distribution appears to be like a Gaussian, and it does approximate the black distribution. While for the model that is homoscedastic, what you see is that in many areas, the uncertainty, or the z-score, is incredibly high, and in many other areas the z-score is incredibly small, meaning that this network doesn't have a well-calibrated uncertainty. This is evidence that uncertainty in this specific application needs to be heteroscedastic, because a homoscedastic model wouldn't perform well enough. You also see here below, in a situation where, for example, you cannot predict what the CT will look like from the MR, this is the rectal region, and in the rectal region, because the images are taken at different points, the ground truth and the ground truth CT and the MR are taken at different time points. Obviously, the presence of gas or stool in the rectum of these patients is going to change depending on how they're positioned and depending on the point in time. And because of this, the model is basically aware, and you see that the uncertainty is very high in that region, is aware that the error that is going to be introduced in that part of the regression is going to be very high, because there is never a way for you to know where the equivalent intensity would be in a CT in the ground truth compared to the MRI, because of this physiological difference that you might have between two images. You can also use uncertainty as an inherent measure of quality control. So the idea is that if you are to use a model clinically, you want the model to have two behaviors, either to be confident, so it knows that the answer is correct, so the uncertainty is low, and in that setting you want the model to act autonomously and to make decisions by itself. And you want the model to also say, if the uncertainty is high, and uncertainty obviously here needs to be well calibrated, if the uncertainty is high, then we can ask for a human being to come in and to help us make a decision. The way we model uncertainty and the way we summarize this uncertainty measure and we make decisions as to when it's safe or not safe can be done either using the uncertainty itself, but we can also, for example, sample from the model and calculate other metrics which are often used in a quality control setting. For example, we could calculate the coefficient variation between multiple samples of the model. We can calculate the dice score between multiple samples of the model. We can calculate the uncertainty, or the mean uncertainty in the predicted region given multiple samples of the model. So all of these different approaches will give you different measurements all of them which obviously will be highly correlated because they all come from the same samples, but they give you different intuitive answers to the problem that we're asking, which is can we know if we can trust a model? And yes, you can use these uncertainties as a way to make those predictions and to use a model safely in a clinical environment. And what's interesting about this method that you've seen before is that if you were to apply it to a real world situation, for example, if you were to calculate the die-score between multiple Monte Carlo samples or the coefficient of variation between those samples, you see that for example, the die-score between multiple samples, which is presented in the plot here on the right, is highly correlated with the true die-score. So the more the samples agree across multiple samples, the closer you are to have a very good performance of your algorithm. So there are very few situations where across all the samples, they all agree with each other, but the die-score is very poor. However, when there is disagreement, which is, for example, any situation where the dice over all the samples is below, let's say, 0.93, which will be this threshold, you'll see that all the die-scores, all the predicted die-scores are quite low. So a cutoff that is used, for example, on the dice between multiple Monte Carlo samples will always give you a reasonable die-score. For example, if you were to cut it around here, you kind of have a guarantee that your die-score is always going to be above, for example, 0.65, which is still quite good in this specific application. Another problem that exists when we're looking into uncertainty as an inherent measure of quality control is that clinicians rarely care about the actual voxel-wise uncertainty. So if you were to present a map like this, they probably wouldn't really know what to do with it. And the reason for it is because they're not used to understanding what it means for a pixel to be uncertain or a voxel to be uncertain. However, what you can do is you can calculate the structure-wise uncertainty. So you can basically integrate what this uncertainty would be for each one of the structures, and you can average it over that structure. And if you do that, you're basically projecting errors that exist around boundaries to a measure of uncertainty that exists at a structure level. And you see that, for example, in this image here, where the uncertainty is quite small and localized at the regions, the level of structure-wise uncertainty or the quality of the structure-wise segmentation is very high, while as the image has poorer and poorer quality, you see that the model immediately realizes that the structure-wise uncertainty is lower, and that's because it's integrating this map here, which has a much more dense measurements of uncertainty because the model is much more uncertainty throughout. The other part that you can do is to use what is called test time augmentation. So we were talking about aleatoric uncertainty as something that is predicted from the network, and aleatoric uncertainty is something that is a function of the data itself. Another way to estimate the aleatoric uncertainty without having to predict an uncertainty per pixel is by introducing ourselves perturbations in the data. So we are asking the model to how it would react to different variations of the input. Obviously, we often do not have many different samples of the same subject's data. And because of that, what we need to do is to simulate those different samples via augmentation. So if you take an image, for example, and you add a little bit of noise, or you blur it a bit, or you change the intensity a bit, any transformation that will still preserve the labels that you want to obtain at the end, any form of augmentation, it will perturb the input data sufficiently so that when you pass it through the neural network, the outputs are going to be slightly different. Even if the neural network was fixed, you didn't have any test time dropout, for example, by doing augmentation at test time, you then are able to get multiple samples and understand what the aleatoric uncertainty is. You can then also merge both aleatoric uncertainty and other types of uncertainty, like the epistemic uncertainty via Monte Carlo dropout sampling, and get an algorithm that has the best of both worlds. And the results that you do, that you receive when you do that, is what you're seeing here. So you see when you're applying only the epistemic uncertainty model, which is what you're seeing here on the left, there are areas, so this is a joint histogram between the predicted uncertainty in the x-axis and the true error rate that is estimated between the prediction and the observations. So when the error rate is high, you want your network to predict that you have a high uncertainty, right? So you want the network to have an uncertainty which is highly correlated with the error rate. But when the uncertainty, the predicted uncertainty is low, you would expect to have very few pixels or voxels with a high error rate. And what you're seeing is if you have only epistemic uncertainty, that the error rate is actually quite high, even for areas of the image where the predicted uncertainty is quite low. When you look at only aleatoric uncertainty, you see that the area here at the top left, which is a problematic area, becomes sparser. And when you bring together both epistemic and aleatoric uncertainty, you basically get an even better result. You also need to take into account that these numbers are log transformed. So there's actually a very substantial difference between these three images, because you're literally going down an order of magnitude in terms of the number of samples with that kind of error rate. We've seen a way to calculate uncertainty and how to use uncertainty as an inherent quality control measure. We're now going to be looking at more advanced methods to calculate uncertainty for medical imaging data, such as ensembles, MHEADs, and probabilistic Unet. Let's start with MHEADs. MHEADs are a model which is really interesting. When you look at a neural network, for example, the one that we're looking at in the beginning of the lecture today, where we were seeing this network that would take a prostate MRI and predict a CT and a segmentation. That network, we call it a multitask network. And we call it a multitask network because we're trying to do two things at the same time, and we're optimizing for two losses at the same time. But what's interesting about that concept is that there is absolutely no reason why we couldn't replicate the task. So that network before was mapping an MR to a CT and a segmentation. But there's no reason why we couldn't, for example, map an MR to a segmentation and a segmentation. And then you might ask, okay, but why would you want to do the same task twice as part of two different outputs of the network? And the explanation for it is actually quite simple. It's because you would like different heads of the networks, different outputs of the network, to converge to different behaviors. And why would you want it to converge to different behaviors? I think that requires a little bit of a drawing here. So if you imagine that you're trying to segment an organ, let's say you're trying to segment a prostate, and the prostate has a certain shape. Let's say the prostate is like a little circle, and you want to segment it, and this is what most clinicians would do. However, one of the boundaries of that prostate might be a little bit fuzzy, and there is another boundary of, for example, of the external capsule of the prostate, which might actually look like this. So if you are now segmenting this prostate, a human would do two things. Either it will segment the inner capsule, which is the part in red, or it will segment the inner and the outer capsule as one. So it will segment it as the green object, if that makes sense. So if you look at this part here, you basically have two decisions that the clinician makes. Either they look at the internal part of the capsule and they segment it there, or they segment the external part of the capsule, but they wouldn't do anything else, right? They wouldn't put the boundary here, or the boundary over there, or even the boundary anywhere somewhere in the middle between these two layers. So the decision to make the boundaries between the inner or the outer boundary, but nowhere else. So if you now have multiple ads of a network, you can have a network optimizing for the green answer, and you can have a separate head of the network optimizing for the red answer. If you now get the output of the one head, you would get the green answer. You get the output of the other head, you get the red answer, which means the same network can now give you two different hypotheses, which is what the MHEADs is trying to do, is a multiple hypothesis network. It gives you two different hypotheses which have converged to different behaviors of the human being. This has been applied, for example, in the context of predicting a CT from an MR, as I was describing before. Here, the idea is that, for example, when you're predicting a CT from the MR, in the MR, if you're looking, for example, at the bone region or at air, they both tend to have a dark signal. So because bone doesn't have any protons and air doesn't have any protons, both the air and the bone have a very low signal in most MRI acquisitions. However, if you look at the CT data, the CT data will be extremely bright in the bone region, and it will be very, very dark in the air region. So now we have a situation where from the MRI, we might not have enough information to figure out if we are in a bony region or in an air region. So we can use m-heads as a way to generate multiple hypotheses. So the different heads of the network could generate different hypotheses where different parts of the body would contain either air or bone in different parts of the anatomy. And the way that you would do this, you'll train a network that makes multiple predictions. So this becomes an n-task network. So this network here has n heads or m heads. And for each one of these heads, we're going to calculate the L2 loss between each one of these heads and the CT. If you were to calculate the L2 loss for all of them, obviously they will all end up converging to the same result because they all receive exactly the same gradients. So what you do is you initialize them slightly differently, which means the predictions are going to be slightly different at the beginning. We calculate the L2 for each one of the outputs, and then we select the head that has the lowest L2 value, and we backpropagate only through that channel. So we end up backpropagating through the network only through the head that has the lowest L2 value for that specific input image example. Obviously, the next time we give another image, a different head will be chosen, and we're going to backpropagate through that, which means different heads are going to start specializing to the different behaviors every time that they have a lower L2 loss, or the lower metric, or the lower loss function compared to the other heads. Another way to calculate uncertainty is to use something called probabilistic Unet. So if you ignore the right part of this figure for now, let's look at the left part of the figure first. The objective here is to segment, for example, a lung nodule, which you're seeing here. And if you ask different humans to segment the same lung nodule, they will create slightly different segmentation. So one of them might do this, the other one might do that, the other one might do that. So they do behave very differently because it's very hard to segment these nodules. The way that you would capture this uncertainty here that humans actually have, one way to do so is to say, I'm going to pass this image through a standard Unet segmentation. But at the very end, I want to concatenate a series of numbers, a vector, which is sampled from a latent space. And when I add these numbers, I want to then be able to, depending on the numbers that I add to this network, depending on the numbers that I concatenate, I want to end up with either that solution or that solution or that solution. So the way you choose which one of these solutions you want is by adding these numbers. Obviously now you can ask, yes, but what are those numbers? How are they generated from? The answer is that there is another network which predicts a distribution of numbers. And this network here is saying, if you're looking at this image, this is the distribution of the latent space that I can predict. And if you can predict the distribution of the latent space, if you now sample from the distribution of the latent space, the different samples when fed into the Unet will give you all these different solutions. So the trick is the prior network is the one that is generating the latent space from which you sample, which when you then concatenate with the Unet, you get these solutions here. You can now ask the question, okay, so but how do I train this prior network? How does this work? And this is where the right part of the image comes in. So what you can do is you can use the ground truth that has been segmented by some humans, plus the image. So you feed the image and the ground truth to something called the posterior network. And the posterior network, its job is to predict a latent space variable z, a single value of z, which when fed into the Unet gives you a predicted segmentation which is as similar as possible to this ground truth. So basically the feedback loop is saying, can you train this network that predicts a distribution in a single sample, which when fed into the Unet can make a prediction that is actually similar to that ground truth. This posterior Unet is going to give you this latent code distribution. And what you can then do, as soon as you have this latent code distribution, is that you can train a separate network, in this case the prior network, that only receives the image as an input and does not receive the ground truth, because obviously the ground truth is not available when you're doing inference or when you're testing it on a new data set. And you try to minimize the distribution shift between these two by using a Kell divergence. So you want to make the distribution that is predicted by the prior network to be as similar as possible to the distribution that is predicted by the posterior net. And when this prior net is able to predict the same distribution here as it is there, then you don't need this part anymore, and you basically just have this model where the prior net is now pre-trained. And that means you can now sample from it and get the distribution over samples. And you see here the effect of doing so. So you see that we drop out Unet, you end up with speckly outputs, and that's because of the nature of these dropout speckly effects. If they were using, in this paper, if they were using, for example, spatial dropout, the results would probably be very different, but they use classical dropouts, and that's why they got these speckly outputs. The Unet ensemble, it gives you pretty reasonable results in terms of segmentation, but they all look very similar. There is very little heterogeneity in the possible solutions. And you see what the different human graders have done. One of them said that there's a big nodule, another one big nodule, another one very small nodule, and a fourth one, actually this is transparent, but the fourth one here is saying that there is no nodule whatsoever. So it did not segment the nodule. You see that with the Unet ensemble, they're all very similar in size. With M-heads, you have a little bit more variability, but not as much as you would have with a probabilistic Unet, where you can have very large nodules, but you can also have no nodules at all being segmented, which is kind of what you would want in the end. You can also look at the latent space. So if you were to sample what the segmentation would look like at different points of the latent space, you see that on the left part of the latent space, the nodule is bigger, on the right part is smaller. On the top part, you have a slightly more rounded shape, and in the bottom part, you have a slightly more elongated shape with a little tail. The last way to model uncertainty in terms of images, at least from the ones that are being presented here in this network, because obviously this is a very hot research topic and new things are happening every year, is to use hierarchies. So if you take this image here and you want to again segment the prostate, which is this object that you see here that has the internal and the external capsule, if you were to take this image and if you were to calculate the uncertainty directly, you'll end up with uncertainty that only exists around the boundaries. However, if you've segmented the prostate ever before, or if you worked on prostate segmentation, you would know that in many situations it's actually surprisingly hard to distinguish between the internal capsule, this middle part here, and the external capsule here in slightly whiter color. These two, in this specific image, they are easy to distinguish, of course, but in many other images they're not. So it might be that the error can happen anywhere in this region. It might be that the user, for example, the rater, completely missegments this region because he thinks it's part of the inner capsule and not part of the outer capsule. And because the uncertainty in a classical setting, the way that we've seen so far, will be mostly localized around regions, you're probably going to miss big parts of these objects. So what you can do is to actually solve the segmentation problem at multiple resolutions. So if you take this image and you downsample it significantly, 4, 5, 6 times, you're going to end up with an image which is very low resolution. So if you try to segment that, you will have this segmentation, which is also low resolution, and this will be the uncertainty of that segmentation. If you go down in resolution a little bit less, this will be the segmentation, and this will be the uncertainty. If you go even less in resolution, you get this segmentation and this uncertainty, this segmentation and this uncertainty, and lastly, this segmentation and this uncertainty. And you see that the uncertainties are pointing at different features in different resolutions. And if you calculate the integral, so if you sum over all of these uncertainties, after obviously you map them all to the same resolution, you can then integrate what the uncertainty would be at multiple resolution levels. And interestingly enough, the network basically looks like a hierarchical Unet with little modules that look like autoencoders. So what you see here is that the segmentation is happening at S1, S2, and S3, so at different levels of resolution. And the uncertainty is being estimated in all of these red blocks, both here and here. And you see that basically your network is able to calculate the uncertainty of the full system, but is also able to feedback what that uncertainty is to the level above. So the next level up is informed by the previous level. So every time you make a prediction on the uncertainty, you're not only predicting the uncertainty of that level, but you're using the information of the level below as a way to inform what the uncertainty of that level should be. So it gives you a much more constrained setting, which also provides better estimates of segmentation and better estimates of the uncertainty. The segmentations that we get out of these models are also quite good. So you see here the phi-seg, which is this hierarchical model. The uncertainty not only is very chunky, and it basically has this behavior that I was explaining before, where the full area or with the external capsule might be missegmented. You see what the human raters have done. They said, okay, in this situation, the external capsule does not exist. This one also does not exist. While in these two, the external capsule does exist and is very small, and it looks like this. You see with phi-seg, you have that level of variability. You see that example here says that there are situations where humans miss-segment or might consider the full prostate to be only the internal capsule, while the other examples here show that you would get external capsule also some other times. You see this uncertainty is much more representative of this setting where the rater might completely miss this big area. While, for example, using the probabilistic Unet, you might still have a lot of uncertainty primarily around boundaries, and you might still miss these large shifts. All the uncertainties that we've seen so far rely on one assumption, rely that the estimate of the uncertainties that we made are of good quality, and they are well calibrated. What do I mean by well calibrated is, if you think about it, we are looking into uncertainty and we're trying to relate uncertainty by this measurement of standard deviation, which if you want, you could convert, for example, into an error bar. So if your error bar is, for example, an error bar of the 95% confidence interval, then you'd expect that the ground truth is within this 95% confidence interval 95% of the times, by definition, right? So if your error bar is too small, then you might miss the ground truth, and the ground truth will not be inside of that 95% error bar 95% of the times. If the error bar on the other side is too big, then it will be more often than 95% of the times, and then we are overestimating uncertainty, which is not helpful. So we want to be able to calibrate the uncertainty so that the right statistics arise from the error bars and the different distributions that we're measuring. An example of this is this paper that was published by Zackit and Rosen in 2018, when they were looking to something called affine scaling as a way to calibrate uncertainty. So this method used the classic homoscedastic heteroscedastic model that we've been looking at so far, and it calculated multiple samples from the model. You can then take multiple, for example, if you look at a single line over the probability distribution over multiple samples, over that line, the probabilities look like this. You see that the lower bound and the upper bound of the probability can be quite different in certain areas, primarily, for example, in this region here or that region there, which is when you're entering and exiting the structure. And this basically tells you that there is an uncertainty in the model. You can then demonstrate that this uncertainty scales. And for example, if you were to add noise to the data, that the uncertainty, so as you add noise when you're going here down, the uncertainty of the predictions also goes down. You see that the uncertainty keeps going up in this specific setting. So that every time we add noise, the uncertainty goes up, and the mean prediction gets fuzzier and fuzzier. But you also see that the model might start underestimating or overestimating the prediction. So you see here, if you were to calculate the volume of the different parts of the tumor that we're segmenting here, the volumes can vary quite dramatically. For example, here with a little bit of noise, all the volumes incorporate the truth, which are the blue lines. You see the error bars are within the truth. Here and here are still fine, but when you get to this third part where there starts to be too much noise, one of the error bars is outside. And you could argue that that might still be okay. So we decided to investigate this further. So what this paper looked at was primarily looking into volumes. If you were to sample this model multiple times and you were to get different realizations of the segmentation, and if you were then going to convert them into volumes, what you would get as results is what you're seeing here. Let's focus only on the top row of this table, because the other ones are just different parts of the tumor. So if we look at the whole tumor, which is the top layer here, what you would expect is that the ground truth volume, which is on the x-axis of all of them, so the ground truth volume and the ground truth volume and the ground truth volume, should have a one-to-one relationship with the predicted volume. So the black line here is the identity. You would expect all the points to be touching identity, because you'd expect all the points to be predicting the ground truth volume perfectly. But what you see that there's a few examples here which underestimate volume, and there's also a couple of examples here, these two, which overestimate volume. This is if you have a single sample. If you now run your homoscedastic plus heteroscedastic model plus epistemic model and you put everything in the kitchen sink together, you would get an error bar that looks like this. So these are the error bars that you're obtaining if you were doing standard uncertainty estimation. But what you see is that there are some situations where it still fails. You see, for example, that that specific error bar is too small, that one there is also too small. And if you actually look at the statistics of all of this, you realize that these 95% confidence intervals don't actually have the truth 95% of the time. They have less than that. So we are underestimating the uncertainty. What you can do is you can apply an affine transformation as a form of post-processing to rescale all of these uncertainties so that they are of the right size and so that they fit the statistics that you would want for the percentile that you target. And this is what you're seeing here on the right, which is the calibrated uncertainty. You see that the error bars have grown, but they've grown only enough to be able to actually fit the 95% confidence interval definition, because that's the one we chose in this paper. Another way that you can do that, rather than using this post-processing affine scaling, is to predict directly quantiles and optimize for the definition of the quantiles immediately. So if you're trying to predict something, like say counting the number of objects in an image, you can then add a upper bound and a lower bound, which are quantiles. Let's say you define these as the upper 95% and the bottom 5% percentiles or quantiles. If you were to do this, what you know is that, for example, for the upper bound, if the upper bound is at 95%, there should only be one example out of 20 that is above the upper bound. And for the lower bound, there should only be one example over 20 that should be below the lower bound. So you can create a loss function, which is a loss function that was proposed in this paper, that does exactly this. And if you were to use this loss function to train this upper and lower bound, what you get is what you have in the next slide. So the task here is to label and to segment these different cells that you see in this image. And there's many different ways for you to do that. You can use labeling algorithms, segmentation algorithms, calculate density, which is the inverse of the volume, and calculate Euclidean distance transform, which gives you these little maps. And depending on how you segment these different cells, you can then apply different paradigms to be able to get a definition of uncertainty. So these are all the different methods that this paper has put together. And the results that you care about are the ones that are in the last two columns. So fcal is how well calibrated the method is, and you would want it to be equal to 0.95 because they were calibrated to have a 95% coverage. So in this specific setting, for example, this one here, the 0.96 or the 0.96 or the 0.93 are roughly the best results. This would be too high and those ones will be too low, for example. So you want fcal to be as close as possible to 0.95, and you see this one and here are okay. But you want to achieve a good calibration without increasing the sizes of the error bars too much. So this is the average width of the calibrated error bars. And you can see that in this method and this method here, which have reasonable calibration scores, the size of the error bars are pretty big compared to the proposed method. So they're 3 times to 4 times, even larger than that, bigger than the proposed method here with the quant algorithm. You also see that other methods can have small error bars. For example, here you see that if you're doing regression and looking at percentage errors, you can get a pretty small error bars, but your calibration is not as good. So if you want to have a good balance between calibration and actually have the best and smallest error bars, you should probably be doing quantile regression explicitly. You also have here the same results, but visually. In the x-axis is the ground truth counts, so how many cells you've seen in different images, and in the y-axis is what is the distribution of the prediction, so how many cells does the model predict. And you see that with the proposed method, because we're directly regressing quantiles, the model actually has well-calibrated boundaries throughout the full domain, and there's only 1 or 2 examples which are outside of the domain, which is kind of expected because we have a coverage of 0.93% of the points, or sorry, 93% of the points, not 0.93. And on the other side, you have the most competitive method, which is DDT with a percentage error. And what you see is this kind of behavior, which is really interesting, where the estimated uncertainty is very small for the small number of lesion counts or the small number of cell counts, but it gets really large on the right side of this graph, which means you overestimate the uncertainty when the counts are very large. And you see that this model here has relatively small widths, which are in average bigger than this. You see the widths here are much more constant, while here the widths on this side are very large. But the coverage and the calibration rate is actually much smaller. It's 0.82. And that's because many of these points here that you see on this beginning part are outside of what they should be, of the bounds that they should be. So actually this is statistically not a very good model. And you see that on this side, all of the points are very close to the median, to the purple line, and very far away from the upper and lower bound. While in this part of the biomarker range, the error bounds are really tight, which is clearly not very natural, given the errors that we're observing here. Okay, so today we've looked into how do we apply uncertainty assessment in a image analysis or in a vision setting. And obviously everything that we learned today is extrapolatable to both 2D, 3D, 4D, or any high-dimensional setting, as long as you can train the models themselves. There are different ways to achieve this, and we've seen quite a few, all the way from M-heads to probabilistic Unet, hierarchical methods, test time augmentation, and etc. And we've also learned that uncertainties themselves are not necessarily well calibrated from the outset. So it might be necessary to run post-processing algorithms, for example, affine scaling or quantile regression, as a way to be able to appropriately calibrate those uncertainties for every one of the models. Excellent. I really do hope you enjoyed the lecture today. And if you have any questions, to either send me an email or post a question on Keats. I'll be delighted to answer them. And I'll see you around.